Thanks. Can everyone hear me? I think it sounds okay. Yeah, so my name is Emerick. I'm a graduate student finishing up at Columbia University, and I wanted to talk to you today about some of the simulations I've been running for my thesis project, introduce to you some of the cool stuff that you can look at with these simulations, and present some of the first results from this work. And so I'm motivated by trying to understand two sort of not well understood and still open question areas in astronomy, which is under the headers of feedback and chemical evolution. In particular, so we know that we need models of stellar feedback and AGN feedback in order to drive realistic properties of galaxy formation and cosmological simulations. But how exactly to do that in detail and how to do that with fully self-consistent models of stellar feedback is still an open question. And part of the difficulty in doing this and addressing this problem is that in order to resolve, let's say, stellar winds and stellar radiation feedback, you need high physical resolution simulations, which is challenging to do. And so in particular, we want to better understand how, in detail, individual mechanisms of stellar feedback against stellar radiation, stellar winds, supernovae, couple to the ISM and drive galactic winds and outflows in galaxies, and whether or not we can actually use self-consistent models for stellar feedback to produce realistic-looking galaxies. And feedback is tied directly to chemical evolution because it's not just energy that stellar winds and supernovae dump into the ISM, they also deposit metals. And so one of the questions I want to address is how do those metals, once they're released into the ISM, how do they mix and evolve within the gas? How do they proceed from sort of hot phases in the ISM in a rich future star formation, which is again tied directly to how the feedback actually operates in galaxies, and how are metals distributed across these phases, and how are these metals removed and injected from galaxies? And so I'm going to argue that in order to model chemical evolution properly in hydrodynamic simulations of galaxies, you need proper models of stellar feedback. In order to do proper models of stellar feedback, you unfortunately need high resolution in galaxy simulations, but fortunately this is something that's possible nowadays with sort of zoom-in simulations of individual galaxies or simulations of isolated galaxies. But the problem with pushing towards higher physical resolution is that our model for stars and star particles in these simulations sort of starts to break down at very, very high resolution. So we treat stars typically as average populations of many, many stars with solar masses, or with masses of 10,000 or 100,000 solar masses in sort of large cosmological simulations. We average over the feedback properties of these stellar populations and the metal enrichment properties of these stellar populations, which at those resolutions is totally fine, but once you start pushing to very high resolution, when your particle mass becomes 1,000 solar masses or 100 solar masses and begins to approach the mass of an individual actual star, how you do this IMF averaging doesn't become entirely clear, and it becomes difficult in order to do these models properly. And so, maybe the naive thing to do, and probably the most expensive thing to do, is to sort of break away from the simple stellar population formalism, and rather than model stars in sort of an IMF average sense, model individual star particles in galaxy simulations. And what this allows you to do is reach a super high fidelity in your physics model because you can account for the feedback, the winds, and the radiation from these stars on a star-by-star basis. And you can account for the chemical enrichment, so the stellar yields from these stars, again, on a star-by-star basis. And the caveat, again, here is that doing this is expensive. It's a bit unreasonable to do this for Milky Way scale galaxies at the moment, but we can do it now for global galaxy simulations of dwarf galaxies, at least. And so using the hydrodynamics code ENSO, I developed a new model for stellar feedback and chemical enrichment to follow these processes in low-mass dwarf galaxies. So we reach physical resolutions of about a parsec in these simulations, and follow individual stars from 1 to 100 solar masses in these galaxy scale simulations. And what that allows us to do is track multi-channel stellar feedback from all these stars, couple this to chemistry to investigate the ISM properties of these galaxies, and also following 15 individual metal species yields as they enrich the gas in this galaxy and enrich the stars in this galaxy. And so we can do cool things like chemically tag each individual star particle in this galaxy, which is extremely relevant now as we have better and better data of both the Milky Way and local group dwarf galaxies of individual stellar abundances. And so the stellar feedback that we include in these simulations, we have stellar winds from both massive stars and AGB stars. We follow stellar radiation, we follow photoelectric heating on dust, we follow Lyman-Werner dissociation of molecular hydrogen, and we follow hydrogen and helium ionizing radiation with adaptive ray tracing radiative transfer, and again, core collapse in type 1a supernovae. And so to give you a sort of a visual image of what this looks like in these galaxies, here's two face-on projections of this low-mass dwarf galaxy that we simulate at sort of an arbitrary point in time, and for physical scale, it's about 250 parsecs. So the total radius of the galaxy is 600 parsecs. The mass of this galaxy is 2 by 10 to the 6 solar masses in gas, and 3 by 10 to the 9 solar masses in the the dark matter halo is 3 by 10 to the 9 solar masses. And so again, this is very, very low mass dwarf galaxy. But what this allows us to do is track individual star particles. So I've also plotted on here, at this point in time, all stars greater than 8 solar masses as individual points in both of these images. And why 8 solar masses is because those are the stars that we actually track the ionizing radiation and the stellar winds from. And we can do cool things like, let's say, look at this dense cold gas over here. We could look at the detailed properties of, let's say, the molecular hydrogen or the H1 properties of this soon-to-be star-forming region that's cold and embedded in hot ISM. We could look at the chemical properties, so like the oxygen enrichment of this cold, dense gas as it's embedded in hot, metal-rich gas. And this is interesting in this dwarf galaxy because it's very low metallicity. And so what the molecular hydrogen formation is doing in low mass, low metallicity dwarf galaxies is still an open question. And if we look again at, say, this area of recent star formation, we can look in detail at the interstellar radiation field. Let's say the hydrogen photoionizing radiation of these stars in this region, the FUV radiation field of these stars in this region. And we can look in detail at, let's say, the nitrogen to oxygen ratio of stars in this region, this green gas, which represents active enrichment by stellar winds, versus this sort of purple gas, which is active enrichment from supernova in this galaxy. And so I just want to give a brief summary of some of the results from these simulations so far. So in a recent paper I put up last week, we've investigated the role of stellar radiation feedback in these simulations. And in agreement with previous studies, we find that stellar radiation feedback is very important for regulating star formation in this galaxy. But a new thing that we've contributed is that we've investigated how the long-range effects from stellar radiation feedback affects galaxy evolution. We find that sort of the long-range effects, so 50 to 100 parsecs away from individual ionizing sources, is necessary to create the right conditions to drive significant supernova outflows from these galaxies. We found that metal mixing and the ejection of metals from these galaxies depends on where those metals come from, whether or not they're AGB winds or supernovae. And the distribution of metals within this multi-phase ISM, even though it's quite complicated, the distributions are broad and they're non-trivial, but they can somewhat be described with analytic models. And so I don't have nearly enough time to talk about all this stuff, so I'm just going to focus on one for now, but you can ask me about the rest later. And so maybe one of the simplest things to look at for this galaxy is what happens to the metals once they're produced. Are they retained into the ISM of the galaxy, or are they ejected from the galaxy in galactic winds? And so we know observationally from dwarf toroidals in the Milky Way and of, let's say, the Leo P dwarf galaxy, which is a nearby gaseous, actively star-forming low-mass dwarf galaxy, that most of the metals in these galaxies aren't retained in the ISM, they're ejected. And so we can look at how that happens in our simulation. You can see this is the fraction metals contained within, let's say, the disk, this dashed line of the galaxy as a function of time. And we see at the end of this 500 million year simulation that 96% of the metals produced in our galaxy are rejected from the ISM, which is in rough agreement with what we see in these low-mass dwarf galaxies. But like I said before, we're tracking 15 individual metal abundances, so what happens to the individual metal species, not just metals as a whole. And so we can look at the fractions of metals contained within the disk of the galaxy at the end of the simulation. And you can see for most of the metals, like oxygen, for example, again, less than 5% of those retained in the galaxy, but for elements like nitrogen and barium, roughly 22% of those metals are retained. And the only differences between these two species, between oxygen, nitrogen, and barium, is where they come from in this galaxy. So nitrogen and barium, for example, are produced almost predominantly in AGB winds in this galaxy, whereas oxygen, for example, is produced almost entirely in core collapse supernovae. And so it actually matters where these metals come from in the galaxy, and that where they come from in the galaxy actually drives what they do in their evolution. And so you expect if they are ejected differently, they may be distributed differently in the ISM. I'm so going to try to maybe gloss over a few things really quick. But we can look at the sort of the metal fraction PDFs, so how these metals are distributed within the ISM. So you can construct a PDF, basically just tells you the mass of gas in the galaxy at a given metal mass fraction, and do some normalization so it looks pretty in a plot. But if we do this for oxygen, for example, we can see this is the distribution of oxygen normalized to the median of the distribution in the galaxy. And you can see something interesting, which is that this distribution is fairly narrow. It's only it's a quarter dex wide. But the full distribution is about 4 orders of magnitude in this galaxy. So the distribution of metals in oxygen, for example, is quite broad. We could break this up into individual phases, like the cold neutral medium, the warm neutral medium, the warm ionized medium, and the hot ionized medium. And what you notice is that as you get to warmer and warmer mediums, the distributions are much broader. And so apparently the colder mediums are more well mixed, than the hotter mediums. And you can compare this again against different metals. So this is oxygen. If we compare this to barium, which is produced mostly in ATB winds in these models, you can see qualitatively that the distributions of barium are quite a bit broader than the distributions of oxygen in this galaxy. And to quantify that a bit more, again, the interquartile range of the coal gas and oxygen is a quarter dex, but for barium, it's 0.8 dex, so it's substantially much more broader. And so metal mixing and metal ejection depends on where these metals come from in this galaxy. And so I just want to leave my summary slide really quick. So we developed a new method for chemical evolution feedback in ENSO, following individual star particles. We can follow ionizing radiation and explore how metals evolve and mix within the ISM and eject from these galaxies, and eventually extend this to more massive galaxies as we move forward. Thank you. Yeah, so in this, I haven't looked at that in detail, and there is some of that in this case. I think answering that question accurately really requires cosmological simulations because the inflow of gas will really dramatically affect what happens to those metals. And since we have isolated dwarf galaxies, I don't have that effect, so I'm not sure exactly in detail what happens in that case. Yeah, so I can look at the plot again, but so a lot of it gets ejected from the velar radius, but most of it gets retained sort of in the halo of the dwarf galaxy. So if I were to keep running this for longer, it may reaccrete eventually. I'm just not sure. Right, so the star formation algorithm, so we have a number density threshold, like you say, and at this resolution, right, an individual cell at the density threshold doesn't have enough mass to form stars. And so when we actually do star formation in here, it's sort of at one lower resolution than that. So we form stars in a 3x3 cell region around a given cell that surpasses that density threshold. And that's how we accumulate enough gas mass to actually do this.
Mass,
right. Yeah, most of it. Yeah. So in this particular model, we don't actually account for any of that stellar mass. And so what that means is that we're generally probably biased a little bit in overproducing more massive stars. And so I have a new sort of model for this that accounts for stars of that mass. True. I don't know if that's, yeah. Yeah, I'm not sure if that's how much that's relevant here. But. I haven't looked in detail at the metallicity going far out into the halo of this galaxy. But the metallicity of the outflow is slightly more metal-rich than the metallicity of the galaxy a little bit. But not, I wouldn't say significantly, just because the amount of mass in metals isn't that great. And there's, again, a lot of sort of other gas getting ejected from the galaxy as well, in addition to just the metals. I haven't looked at the turbulence in detail in the simulations yet.